All right, so in this next example, we are going to take just a closer look at our example 2, where we were looking at the height and the weight. We did this, we put these values in a stat crunch, we also calculated this by hand. So if x equals height and y equals weight, then r equals 0.881. This was our original data set. This is the r that we see in this first table. Notice that if we take this table and we switch these, and we make x weight and y height, right, our graph is going to, our scatter plot is going to look different. Our equation of our line is going to look different. But notice that our r has not changed. It's still the same. So we're just going to make a little note here. Switching x and y does not change r. All right, if we add 3 inches to each woman's height, so we've taken our original data set, our original height was 61, we added 3 inches to get 64. We didn't change our weight. Excuse me. We didn't change our weight, we just changed our height. Notice that our correlation coefficient is the same. So we will say that adding a constant is just a fancy word for a plain old number, no variable or anything. So adding a constant, and this also is going to be true if we multiply by a constant. There's not a table for this, but it is also going to be the case. Or multiplying by a constant also does not change r. And then what we see in kind of this paragraph below, this is a little more information about our correlation coefficient, including the stuff that we just looked at. Changing the order of our variables does not change our correlation coefficient. Adding or multiplying by a positive constant does not change the correlation coefficient. So what that means is our linear correlation coefficient is a unitless measurement of association. So kind of like our z-score, we don't have any units labeled on the end. Right, we just have r is equal to some number. Our correlation coefficient is not resistant, right? Since it is based on the mean and the standard deviation and not the median and interquartile range, it's not resistant. So an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. So basically, if we had some either extremely small or large outliers, values that don't fit in with the pattern, then our correlation coefficient could be affected by these outliers. Right? And then last but not least, just a reminder that correlation is not causation. Right, so in example 4, we are going to look at this example. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the parentage of births to unmarried mothers since 1990 is 0.940. Does that mean that a higher percentage of females with bachelor degrees causes a higher percentage of births to unmarried mothers? What we want to look at here is we want to look at that word causes. Right, so just because we have a large number here, we cannot use this word causes. Right, correlation is not causation. Right? So there's going to be some sort of linear association if we were to graph these data sets, but that doesn't mean that one data set necessarily causes the other. Right, so the answer to our question, does that mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers? We are going to say no. All right, correlation is not causation. All right. The correlation exists only because both both percentages have increased since 1990. So one doesn't cause another. There's correlation simply because both value data sets have increased. Right? So I'm going to add one more little thing down here at the bottom. We cannot claim causality between two variables we can only claim causality when the data are collected in a controlled experiment. All right, so nothing has changed since our first chapter, right? Since we looked at controlled experiments. Controlled experiments are the only way that we can explain causality, right? Correlation is not the same thing as causation. So as you're going through and you're working through the problems and you see something and you see the word causes in there, right, make sure that you stop and think about what the question is asking us.